The first thing we did for our project was to talk to a professional named Jesse Martin who owns his own air conditioning service company here in Tyler, Texas. He told us that he had done a geothermal project where he ran clean water underneath a pond and then back to a house using that to air condition the house. He said that project would cost about $40,000 to $50,000, while a regular air conditioning unit would cost about $15,000 to install. But because it's our project, we continued on. And we have a little bit different of a system. We have air going under the pond instead of water. So in order to see what it would be like, we looked at the properties of a pond, how cold it would get, and learned that you don't actually want a pond to do geothermal air conditioning. You want a lake, because a pond is classified as a body of water that allows sun all the way to the bottom, therefore allowing vegetation and stuff to grow up. That means that the temperature of the water is pretty generally around air temperature. Lakes, on the other hand, have 3 different layers, depending on how deep the lake is and what place it is. The first layer has about the same temperatures as a pond. The second ranges between the temperatures of the near air to the temperature of the third layer. And the third layer is generally about 8 to 4 degrees Celsius.
Because we weren't given any dimensions for this project, we had to make a few assumptions to get going. So, based on our research, we found that the hypolimnion layer, the cold layer of the lake, usually starts at about 30 feet below the surface. So we decided to assume that was at that depth, and then we set our house 30 feet from the edge of the lake, because that seemed like a reasonable assumption to make. And then we assumed that the lake bed receded at about a 30-degree angle downward from the horizontal. And so this air conditioner has a cooling capacity of 54,000 BTU per hour, which corresponds to almost 16 kilowatts, and it uses 4.2 kilowatts of electricity. Another assumption we made is that we wanted to cool the house from around 80 degrees Celsius to around 62 degrees Celsius, and because that corresponded to 300 Kelvin to 290 Kelvin, which would be nice numbers to do calculations with, and it seemed reasonable for our scenario. We used the equation the rate of change of energy is equal to m dot U2 minus U1. Because we are assuming constant pressure, to simplify the assumptions, we're assuming that the flow is incompressible and at a constant pressure. And so we're able to set this change in energy, or the energy rate, to our negative 15.826 kilowatts. It's negative because we're cooling the system here. And from tables, we were able to find the values of U1 and U2 at 300 and 290 Kelvin. And from that, calculate our m dot at 2.21 kilograms per second. We found this equation for the heat transfer coefficient of flowing air. And so it's equal to 10.45 minus the velocity minus 10 times the square root of the velocity. So the issue with this equation is that it is empirically derived and only valid from 2 to 20 meters per second. For the area, we were able to plug in pi times the diameter times the length in the hypolimnion region, which would be kind of like the inside surface area of that pipe. That would be interacting with the water and transferring heat there. Plugging in those values, as well as the difference in temperature, we assumed, because the water could be between 4 to 8 degrees Celsius, we assumed 6 degrees Celsius, which is 279 K, And then to simplify calculations, we used the average value of our two temperatures here, so 295 Kelvin. So from this, we were able to determine that the diameter had to be 0.342 meters, which equates to 13.46 inches. We have the cost of the fan, the cost of the pipe, and the cost of the insulation. They add up to $6,919, which is significantly more than the cost of the central air system. So the central air system uses 4.2 kilowatts and costs $2,300. Our system uses 1.2 kilowatts, but it costs $6,900. So the difference in price initially here is $4,500, but there is an energy savings of approximately 3 kilowatts. So in conclusion, our alternative system would be much more expensive to put in because we didn't even consider cost of installation, which could be done by hand or without hiring someone to do it because it's a very custom system. But there would still be a lot of time involved and potentially additional costs, such as fittings to attach the pipes to the fan, or however the fan is going to be attached to the house, if a hole needs to be cut in the side of the house or whatever, and also potentially weighing down the pipe to make sure it doesn't float, and things like that. But if the system would work and if it would cost that much, and if it would not break or need repairs, then it would pay for itself compared to the Goodman central air system in just under 6.5 years.